In our daily life, we have come across circular shape in a giant wheel, a clock, and a bicycle. The outer frames of a giant wheel, clock, and bicycle represents a circle. Have you closely observed a giant wheel in an amusement park? The passengers of the giant wheel represent a set of points in the plane which are equidistant from a particular point. The passengers would be forming a large circle around a fixed point. Now, let us recall all the basic terms related to circles. Observe these line segments carefully. What is the difference about them? In figure 1, the line PQ and the circle have no common point. Hence, PQ is called a non-intersecting line with respect to the circle. In figure 2, there are two common points A and B that the line PQ and the circle have. Hence, in this case, we call the line PQ as secant of the circle. In figure 3, there is only one point A which is common to the line PQ and the circle. In this case, the line is called a tangent to the circle. Where have you come across tangents in real life? Take a look at the pulley made from wheel and a rope which is used in lifting objects. Observe the position of the rope with respect to the pulley. The rope on both the sides of the pulley represents a tangent to a circle. The wheel of a bicycle which moves along a line is a tangent to the circle. So, a tangent to a circle can be defined as a line that intersects the circle at only one point. How do you demonstrate the existence of a tangent at a point? Let us do an activity by rotating a secant AB about the point P and observe the changes. When we rotate the secant about the point P, the point Q comes nearer to the point P. As we rotate further at one stage, the point Q coincides with point P. This shows that a tangent exists at the point P on the circle. On rotating further, the line begins to intersect the circle at 2 points. What do you conclude from this? There is one and only one tangent at a point of circle. In the activity, we observe that as the position of AB moves towards the position A-B', the point Q1 on the line AB of the circle gradually comes nearer and nearer to the point P. From this, we can conclude that the tangent to a circle is a special case of the secant where the two endpoints of its corresponding chord coincide. The common point of the tangent and the circle is called the point of contact, and the tangent is set to touch the circle at the common point. You have seen the wheels of a moving bicycle. Do you see tangents anywhere in it? Take a look at the bicycle wheel and observe its position with respect to the ground. The wheel moves along the line which is tangent to a circle. The spokes of the wheel are along its radii. Can you determine the angle that the spokes of the wheel make with the tangent of the circle? To find this, let us represent the center of the wheel as point O, and let xy be a tangent to the circle. Let Q be a point on xy other than P. Join OQ. Where does the point Q lie? If the point Q lies inside the circle, then xy will become a secant and not a tangent to the circle. So, the point Q must lie outside the circle. Therefore, OQ is longer than the radius OP of the circle. What do you conclude from this? From this, we conclude that OP is the shortest of all the distances of the point O to the points of xy. So, OP is perpendicular to xy. Therefore, the tangent at any point of a circle is perpendicular to the radius through the point of contact. Suppose a line is drawn through the endpoint of a radius and is perpendicular to it, then how do you prove that it is a tangent to the circle? Here, it is given that OP is a radius of a circle with center O. Line XPY is perpendicular to OP. To prove that XY is a tangent to the circle at the point P, take a point Q different from P on the line XY. Among all line segments joining O to a point on XY, OP appears to be the shortest. This implies that OP is less than OQ, that is, OQ is greater than OP. So, Q lies outside the circle. Thus, every point on XY other than P lies outside the circle. This shows that XY meets the circle only at point P. Hence, XY is a tangent to the circle at P. So, we can conclude that a line drawn through the endpoint of a radius and perpendicular to it is a tangent to the circle.